Madrid and Codemotion. It's really nice to be here. And so Thomas, you look a little bit unironed, I would say. So our bread and butter job at TNG is typically agile software development, or working on AI and DevOps and cloud and stuff. But we have something which is a bit different.
Yeah. So 10 years ago, Martin and me founded the so-called Innovation Hacking Team.
Yes.
And we did crazy...
By accident, to say so. And so that you have a better idea what we've done back in the days, it was in 2013. We controlled quadricopters with bare hands. We built an augmented reality headset with which you can see the world through the eyes of a Terminator. And here, Project Avatar. With Now and with the Kinect, we were able to control this robot by gestures, with HoloLens and stuff like that. And this is much fun, and we want to present some of these things. So, Thomas, why do we work on such stuff?
Yeah, normally we work on such things because we want to gain new skills. So our bread and butter job may be for customer projects where we don't really know exactly where we don't have the cutting-edge technology available. But if we just want to train ourselves, the best way to do this is by trying it out. We also want to inspire people today and on other days as well. So we want to talk about that on job fairs, on conferences, and so on and so on. And the most important thing is, because we can, because it's possible, because we have the possibility in 10% of our working time to really spend this on innovative projects.
Yes. So, question to the audience. What do these works of art have in common? So this picture, for example, or this one. I will uncover that. So actually it was generated with a text-to-image AI. Probably this is not very new to you, but let's have a look to the prompts here. An oil painting of Obi-Wan Kenobi. Yeah, awesome. Or Jesus on the steering wheel of a Ford Mustang. Generated with Midjourney, by the way. Or here, Boris Johnson with a Pinocchio-alike red nose. Okay, one more. So this is Jesus winning a dance battle against the super devil in a moody black hip-hop club mosh pit with cinematic lighting 1920 colorized. So, as you can see, our focus shifted from 3D cameras, robotics, and stuff like that, just to AI. And this is what we want to talk about today. Let's have a look to the agenda. Artificial intelligence, computer vision in a nutshell. We want to show you how deep neural networks work under the hood. Then we show some showcases like real-time style transfer, real-time deepfakes, a shitposting AI, and so on. So it was in 1966 when Joseph Weizenbaum published ELIZA, and this was one of the very first chatbots, and we have a demo on that. Let's have a look.
Our first demo for
today.
Do you want to do the talking and I can do the typing?
Mm-hmm. Okay. What we see here is Eliza is now telling us, is something troubling you?
Yeah, and then I say, I am at the Codemotion conference, and she says, do you believe it is normal to be at Codemotion conference?
What do you think? Is it normal?
Just type in yes.
Let's type in yes, and create output, and it says, you are sure? And I say, yes, and she says, I understand. Okay. We stop here. So back in the days, this was one of the most famous chatbots, but you probably agree with me, this doesn't sound very, dynamically enthusiastic and stuff like that. How does ELIZA work under the hood? Yeah, if you have a sentence like, I must say you are a robot, so my user input, I type it in, then there will be some kind of a pattern matching, and there is an array with some rules, how to react on specific input sentences. So, like this one, star, blah, 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 you are, blah, 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 and then you just make a pattern matching, and then you can just pick a response rule, like for you are, blah, blah, blah. What makes you think I'm a robot? Do you sometimes wish you were a robot? And so on and so on. Yeah, so artificial intelligence, wow. Nowadays, things work a little bit different. So 2006, in the University of Toronto, deep neural networks were described, and since then we had an explosion of artificial intelligence apps. And the question is, in the meantime, we had a few AI windows, so the money was stopped, conferences were cancelled, and so which path do we take? Do we take the green path, the yellow one, or the red one? So is it a hype, yeah? Or is it something like brace yourself, winter is coming? Or is it more of a summer? And hopefully this talk helps a little bit to get an idea.
Yeah, but first let's have a look at one of the earlier examples of how we did something like face detection back in the days. When computer vision or when the CPUs were not that powerful, we had to do it anyways, and we had to recognize things like faces. Back then, we used things like HAR cascades. HAR cascades normally come with a predefined set of features, like vertical lines, horizontal lines, or something like that, and then they learn how to how a specific shape is shaped out of these specific features, and with that you can then come up with an intelligent algorithm which is incredibly fast and which can match, for example, a face. So here you can see Martin in like 6 dimensions or something like that.
Yeah, that is really tricky.
But as you can see, the illusion breaks pretty much immediately if something is in the way of the face. So if Martin is looking sideways, or if he holds a hand in front of his face, the illusion immediately breaks. So this is not very robust, but it's very fast. And this is how we did it for a pretty long time. Yeah. And this is how Martin looked for a pretty long time.
Yeah, so you can do it much better, right?
Yeah, exactly.
How can you accomplish that?
Yeah, neural networks, of course. And for that, we'll have a very short introduction into how neural networks work. So normally, neural networks are inspired by nature. And inspired by nature means it's inspired by the human neuron, and the human neuron basically exchanges electrical signals. So we can, for example, just collect some stimuli from the surrounding neurons, and if this potential is high enough, the action potential is there, and the neuron fires and signals to the next neurons using electrical signals. And if the stimuli are not high enough, then we have a so-called failed initiation, and basically nothing happens. So you could say this is a 0 or 1 function or a cutoff function. And some brilliant mathematician just thought, hey, we can model this, we can put this into a mathematical model, and there we have it, our artificial neuron. So the artificial neuron basically works pretty much in a similar way as the real neuron does. It takes some inputs, so in this case it's only 1, x 0. Then we weigh this information with some specific weight for the connection, which is omega 0. Then we add some bias, which is basically the reactivity of our neuron. We put that through an activation function, which could be our cutoff function, so 0 or 1. And then everything goes to the next neurons. So
we took all our money and made this beautiful animation here.
Yeah, and
this one.
And here you can see, the more, the higher the value for the weight, the more important the information gets. And we then sum up everything that we get as an input. We add the bias, we put it through our activation function. Could be something else, not only a cutoff function is possible, and then we put it to the next neurons.
Right, and now the question is, so obviously this is working with numbers, yeah? So how can we translate something like this one, a 20 by 20 pixel field with a face on it, how can we translate that to numbers? Well, it's easy. If you have this grayscale picture, you just could say, if there is a white pixel, it's 1.0 the activation, and if it's a black pixel, it's 0.0. And everything in between, you can see it in this slide here. And so all those pixels, they get their grayscale color number activation. And the magic is what you can do right now. You take the pixels from 1 to 20, 21 to 40, and so on. So you have a large line of those grayscale values, and this is our input vector, so 400 pixel activation numbers, and this goes into the layers of our deep neural network. So it starts with layer 1 and layer n and so on and so on, and after that we would expect that this deep neural network would say,
This is a face.
is this a face or not?
And interestingly, somehow our neural network mimics nature here in that it recognizes simple features in the first layer, so something like a line or something like that. And the deeper you get, the more complex the shapes get
Yeah.
that the neural network can recognize. And these are features, they will be important in the future slides.
Very, very important, these features, and they are self-trained.
Yeah, exactly.
They are not hard-coded. So what happens if you take a duck now as an input, and then this goes through our deep neural network again, and hopefully it says, well, to 0.23, so you could translate that to 23%. This is a face, so yeah, it's not a face, that's good enough for us. But sometimes it can happen that a deep neural network says, well, 82%, this is a face. And our typical reaction is, this is not good. What do we have to do, Thomas?
Yeah, so now we have to punish our neural network.
And how do you
we
punish?
can punish our neural network the same way we would punish humans, namely by money. So we define now a cost function which basically takes the real value. So we know that this is a face, so it's a face for 100%. And we subtract whatever the neural network put out. So this is 82% in our case. We square that up and we add all of our inputs together. And then we have a cost function, which in this case is 0.03, so the amount is pretty low. But if we have something like the duck in this case, so this is definitely not a face, so with 0% it is a face, and we can then subtract our value from our neural network as well. And if we square that up and take the cost function again, we see that the value is much higher. So what do we have to do?
And with this you can train your deep neural network. So you have the loss function values, and with the optimization method, like for example gradient descent, you can just optimize your model, and that's the magic. So just think about going back to the artificial neuron, those weights and those biases, like synthesizer knobs, yeah? So you just turn them and you manipulate the artificial neuron in this case. But there is a huge problem. Think of an aperture, a machine with millions, if not billions, of such wheels, turning knobs. So you don't know where to start. And yeah, if everything works well, we have now a short classification demo, and let's start with just standing in front.
Yeah.
You can see lab coat, Windsor tie, stethoscope, probably because of this badge here. And what do we have here? A packet, Band-Aid,
Yeah, sure.
a syringe, okay, yeah. Because of the lab coat, probably. So this is VGG19. It's a very bad deep neural network, but it's efficient, right?
It is kind of efficient, and also the thing that we showed you here, this is a neural network that doesn't only tell you is there a face or not, it tells you a bunch of different classes. So I think it's 10,000 different classes. And right now, Martin is obviously a racket.
Yes,
and one
I'm a
fun thing
racket.
that you can do with this VGG19, because it's so fast, and it may not be the best at like describing what's going on in the scene, but you remember the features that we had earlier. So in the layers, those learned features that kind of give us an idea of what is going on in the image, we can now do the following. We can take an image of, for example, Martin, and we can shove it through the neural network, and then pull it back again and say, okay, whatever you saw in here, enhance that. And that's what we can do, going through different kinds of layers. And you saw in the beginning, we get very abstract shapes in here. And the deeper we go into the neural network, the more concrete we can now make out some weird things that kind of look like dogs and birds and dog birds and fish and everything. And all of that is kind of hallucinated into that image.
But why?
Of Martin. But why? Well, basically...
It was trained. Maybe.
Yeah, because the VGG19 that you see has been trained on like a bunch of different things that it should classify, for example, a lot of animals here. So what it learned in there is to kind of understand how animals look like and to look out for that. So if we turn that around, we can produce...
Yeah, and now that we have a deeper understanding of how deep neural networks work, we can have a look to the real-time style transfer. So what is a real-time style transfer? We have this beautiful painting of Van Gogh, perfect, Starry Night. And we have a beautiful photography from me. So this is the Mesa Arch in Canyonlands, USA. Very nice place. And now let's have a look what happens. So now it looks like that Van Gogh was painting the Mesa Arch. He was there, but this is not the case. So what is a style transfer? You have a content picture. This is the sandstone sculpture there, the rocks. And then we have a style, which is the Van Gogh painting, and you create some kind of a pastiche. Yeah? And typically, this is a post-processing approach. For one picture, it takes just 3, 4, 5 minutes or something. And we made that real time. So we need to train our network, of course, again, loss functions. One is content loss. We totally accept that our style transferred picture will lose information. Yeah? How can we calculate that? We have a look to a very specific point, here in this case, in the picture, in the original content picture and in the style transferred one. And then we just compare them. And there is a specific sweet spot where we say, okay, we accept a specific content loss, we can use the feature activations we already told you, and we can press that into a coast function.
But we also need something else, because we
Right.
don't only want to reproduce the content, but we also want to reproduce the style.
Yeah.
And in order to do that, we have to do pretty much the same, but now without a specific regard to the location of a specific feature. So for example, we could have something like the star in the Starry Night, and we will find the same feature somewhere else in the picture as well, but it doesn't have to be the same location anymore. And with this, we can now define a second loss term, and then we have some, as Martin said, some sweet spot between content loss and style loss.
And fun fact about those features that we talked about, those are once again from the beautiful VGG19 network that we just saw earlier.
Yeah.
So you can also use it for artistic style transfer.
Yeah, you can do crazy things with that. So it's not that bad at all.
Let's do some crazy
Yeah,
things.
and so this is a picture of, and now I have to ask you, please.
Giacomo Balla.
Giacomo Balla. Yeah?
Yeah.
Giacomo.
It's an artist from?
Italy.
Italy, okay. So this is a picture, pessimism and optimism. So let's have a look to this one. And now you can see this
Looks very artistic,
Yeah.
actually.
Yeah, and actually what we did, we have a HTC Vive Pro, and we film the environment, and then everything gets style transferred.
Oh, let's have a look at some other
Yeah, so it's like an LSD trip without
without the cost. Yeah.
the cost. Yeah.
Right, what else do we
So
have?
what is that, Thomas?
Piet Mondrian. So if you put in some very abstract paintings, then some very abstract pictures will get out of that. Isn't that beautiful?
Okay, let's have a look. We have some other styles here in this case.
Need to be a bit quicker, but let's just go to our lovely...
The best one is this one. Maybe the audience. Oh, yeah, this is also cool. Yeah,
Almost like the original.
Yeah. And this one. So what is that?
Who knows this one?
This is taken from a music video. It's from Aha, Take On Me. And actually we trained our deep neural network for 3, 4, 5 hours something. And since then it's able to do this stuff in real time. Isn't that amazing?
Cool.
And this brings us now to real-time deepfakes.
And there will be a lot of demos now. But first of all, let's have a look at what a deepfake actually is. So a deepfake basically means you take a face and you put the facial expression onto another face. So in this example here, this is a real-time deepfake. So in real time, we took the facial expressions of Dirk Steffens, which is on the right here, and put the face of Harald Lesch onto him. So you can see Harald Lesch, which is a famous German science guy, and you can see him on the left and on the right here. But only one of them is real. So in order to do this, in order to have this effect, we of course need to first do some calculations, because we need some multiple steps to get from an original image to the final result. So the first we have to do is we have to do a face detection. Face detection basically means we detect, we use a library called MediaPipe. With that we can then identify 468 landmark parts.
You won't believe that. We have a demo on that.
Actually we have. So here you can see Martin's face, and you can see, yeah, there are lots of landmark points on his face, and this looks pretty interesting. And with that, we can now define where the face is located. But this is not enough, because we want to replace the whole head. So Jonas, what do we have to do?
Yeah, so the next thing that we have to do is we kind of have to figure out where exactly is the face, what pixels belong to that, where's the hair, where's the ears, and for that we're using a second neural network that does a so-called segmentation. So that tells us for every single pixel, is that part of the face or not?
You know what?
What?
We have a demo on that.
Oh my God. All right, okay, perfect. So here you can see live segmentation running on Martin.
This is really like the Blue Man Group, right?
Yeah, this is basically the Blue Man Group. We decided
Too
to
much
turn
beer yesterday, yeah.
all the pixels that belong to Martin's face blue. And you can see it works in real time. When he turns his face sideways, it kind of breaks sometimes. It works actually quite well. And the reason for that is the segmentation network that we're using here, we trained on a bunch of celebrity photos, and it turns out celebrities never look into the camera sideways. So that's why it doesn't work too well when looking into the camera sideways. Thanks you, Martin, for this nightmare material. Okay, so why did we even find the pixels in the face? Well, we don't want to see the old face anymore. For this reason, we do something that is called inpainting. That's a technique that you usually would use to repair old pictures by removing scratches. And in this instance, what we're doing is removing giant scratches.
You know what?
What?
Demo.
All right, let's have a look. Okay, and here we can see we're basically removing the biggest scratch that Martin has, which is his face. And it's not there anymore, which is great, because that's exactly what we wanted. You can see it's not working perfectly. It's not looking absolutely legit. You can tell that something is going on with his face. If I put my fingers close, you can see they get pulled in. What we're using here is actually
That's uncanny.
is actually a technique that is kind of similar to how fluid dynamics work and stuff. So the results aren't perfect, but they don't really have to be, because we're supposed to put another face in there as well. Isn't that right, Thomas?
Yes.
Yes, exactly. And now, we'll get to a slide that didn't age that well. Back in the days, we really thought, when it comes to TV, it's always good to have a face that is similarly shaped to Harald Lesch. So let's take Putin.
How funny.
This was in 2021. In 2022, we thought, okay, this might not have been our best idea so far. But anyways, nowadays we would rather have something like the future Prime Minister of the UK in there, so at least more competent. Now we can. Now let's have a look at how this works internally. At the heart of each deepfake, we have a so-called autoencoder. An autoencoder is basically a neural network, which in our case takes an image, then puts that through a layer, a few different neural network layers. So in this case, there are two different parts to it. The encoder takes that into a latent space representation. Latent space representation is then basically a compressed version of the face, where you can see things like, is the mouth open? Are the eyes open? Is the person smiling? So things like that might be trained into our latent space representation. And then we can take the decoder to re-encode our image from the latent space and get the exact same image out of that again. But at the beginning, here you get just white noise, so we need a cost function or a loss function again. So what we now need to do is basically just take the pixel difference between the output and the input, and with that we can now train our neural network, and what we get is a beautiful autoencoder which can take in an image of Harald Lesch, recreate the exact same image again.
That's so exciting.
That's totally lame.
It is exciting, at least if you put in a trick. So let's take two of these autoencoders, so one for Dirk Steffens and one for Harald Lesch. And now we take the face of Harald Lesch, we put it through our encoder into our latent space representation, where we find things like, is Harald smiling right now? And then we take the wrong decoder, namely that of Dirk Steffens, and we get the face of Harald Lesch, but with the face of Dirk Steffens, sorry, but with the facial expressions of Harald Lesch. And this is how deepfake works at its core.
And guess what?
Not again.
No, he didn't do it. Okay.
Hi,
Who are you, Martin?
I'm Brian. I'm the spokesperson, I think, from Fujitsu, right?
You used to be, at least, yeah.
Yeah.
All right, do we have any other faces in here?
We can try.
Yeah, I think we have a few.
Okay, who's this?
This is Markus. It's a friend of us.
Yeah.
Okay.
Now you can bring him everywhere.
Yeah.
That's a very cost-effective way to bring your friends. And then here we have another person that we are for sure allowed to show his face. What else do we have? Yes, and we have this person as well. So what you can see here is the deepfake basically works now for any face shape, for any gender, for any ethnicity, and that's exactly what
There is a problem with the demo. Look at this. I'm putting out my tongue.
Yeah, Martin is sticking out his tongue. It doesn't work in the deepfake. Why is that? Well, we're still using media pipe face mesh. Media pipe face mesh doesn't detect the tongue. And also, when you tell people to give you video material to train your deepfake on, nobody also sticks out the tongue in there. So it's only the people testing out the deepfakes.
Right.
Isn't that amazing?
I like how the deepfakes get worse.
Yeah. That's kind of uncanny.
Very nice.
So now we've seen what AI can do in the visual domain. But let's talk about human language and text now. So when it comes to human language, what we talk about is normally natural language processing. And as you can see here, it's basically, where linguistics and computer science meet. So that means whenever we're processing human language in a computer, whether that be text, for example, whether that be voice, that is natural language processing. And there's a bunch of different fields of applications for that. So, for example, here's a couple of them. If you've ever used your voice assistant on your phone, you say something that gets translated into text, then it comes up with some kind of answer. It might do a lot of things like retrieve information, extract information, or just answer a question from its knowledge and then read that back out to you. And all of those things where we process human language, that is exactly what natural processing is.
This we have to turn text into numbers.
Yeah, because that's
but how does that work?
Yeah, that's the big problem, because human language is in text. We already told you how neural networks work with numbers. So now we have to turn text into numbers, and that's what we call tokenization. So here you have the sentence, for example, that is a string. Computer science is so nice. Something that we would for sure all agree on. What we want to do now is just to split up this sentence into different so-called tokens. Martin?
Mm-hmm.
And you can see it here. Now we split up our string into a list or a vector of 6 so-called tokens. These can be words or subwords. So for example, we have here computer and science and is and so and nice. And the thing that we can do now is to assign each of these tokens, once again, a number. So computer obviously becomes 42, and then science is 23, 101, and then both so's got translated to a 3. So it doesn't really matter where they stand. Tokens always get the same ID. And yeah, this would be so cool if we had a demo for this, right?
Yeah, I have one.
Okay. Perfect. So what Martin is going to show in this demo now is it's the most exciting demo that we have. In this one, we are going to live tokenize a sentence for you.
It's awesome. Wow.
So for example, here we have welcome to the Codemotion conference in Madrid. And that is going to be tokenized into exactly those words. Even the exclamation mark is going to be its own token, and that is, for some reason, token 0.
One interesting thing is that Codemotion got split up into 2 tokens, and this is because we cannot just assign to each and every word that could possibly exist a number. So if we have, for example, in German, there's a real word called Donaudampfschifffahrtskapitänsmütze, which is a real word, and this you would not have as a specific token, but a number of tokens.
Yeah, but now we have turned our string into a list of numbers, which is exactly what we need to feed into a neural network. And one thing that we can do now is we can just take this as an input vector, we can just pad it for the values that we don't have, and shove it into a neural network. And this can, again, be, for example, a fully connected neural network, and then we can just tell it, give us, please, the next probable token, for example, it.
And why do we discuss this?
Well, kind of natural language processing is kind of important to understand how we build the shitposting AI. Because that is something that is very dear to our heart. Why did we build it? Well, turns out if you build style transfer things and deepfakes, if you go out there on the internet, there's going to be a lot of people who will always want to comment on this. And this is just kind of annoying for us because on our end, we always have to reply to that. And over the years, we realized, well, we now are spending a lot more time discussing with people online rather than doing cool stuff. And we found, well, we are kind of stuck in a cycle, and we call that the shitposting cycle. So on the left, on the right, actually, you can see like a typical internet troll commenting on one of our showcases. That is a shitpost. And on the left, you can see the average TNG consultant who then has to reply to that. And that's not where the story ends. Nobody on the internet ever changes their opinion, so the shitposter then answers back, and it goes on and on and on, basically forever. And then we thought, okay, maybe we could do something better with our time if we just automate that part away, where we have to reply to the shitposter, and then maybe we can make the shitposter's life a little bit better by just automating his part away as well and just taking the human completely out of the loop. And we end up with something that looks like this. Here we have this floating NLP brain thingy that is going to create a shitpost and then reply to that and reply to itself in eternity. And that's what we wanted to do with the shitposting AI. And for that, we chose a very special small neural network that you might have heard of. It's from like this AI startup that is called OpenAI. And the neural network itself is called GPT. And GPT stands for Generative Pre-trained Transformer. And that's also the exact reason why we're using it here. So to break it down, generative means we are now generating new text. So we could generate shitposts, for example. We're not doing classifications as we've seen before. Then pre-trained means it comes pre-trained on like a large internet corpus. It knows how language works. It should also always be right because it understands the entire internet. And transformer doesn't mean that it's Optimus Prime, unfortunately. That is just the very special architecture that we're using here to make it so powerful at understanding text. And we want to have a look under the hood of what exactly makes the transformer so special, what the secret sauce really is. And the secret sauce here is called attention. And you can think of attention as kind of in the same way as cheating works back in the school day. So imagine this, you're sitting in the middle of a surprise test that obviously you didn't study for. So what do? You don't have the information to fulfill your objectives, so you have a little look to the left, you have a little look to the right, you gather the information that is most relevant to you, and you take that information and you bundle that on your piece of paper. And that's exactly how attention layers work in transformers such as GPT. Let's have a look. So now the transformer's task might be to understand what exactly this token he means in a sequence. So what does it have to do? Well, it looks back in the sequence, and there we can see, well, he obviously refers to the shitposter's mad full stop he. So what the attention does here, it identifies the tokens that are most relevant to understanding he, and those are going to be shit and poster and mad, obviously, and he as well. And then it takes those and bundles them into the output, where we now get something that is at least a bit more telling than he. Now that we've understood how transformers work and how GPT works at understanding text, now let's have a look at how they generate text. Because if you've ever used ChatGPT, for example, then you'll know it generates text token by token, and it does so in a so-called autoregressive next word prediction. And it kind of looks like this. At the beginning, we put in one token or multiple tokens, and we're going to run those through GPT, and what GPT is going to give us is the prediction for a next token. So after computer, we, for example, get out science. And that is basically what GPT is going to give us here. If we want more tokens, we have to put the output back into the input. So if we now put in computer science, we'll get the next token, and that is going to give us is. And we continue with this on and on. We get cool. And after cool, we get a so-called end of text token. That's basically GPT's way of telling us it's done generating a text for us.
Yeah.
And yeah, we have another demo that we're going to skip because it's boring. And now instead, think about, okay, we now want to create our shitposting AI. What model could we use? And back when we did this, we had two models to choose from, GPT-2 and GPT-3. GPT-3 was the way more powerful one, the bigger brother, so to say, that you could use through the API of OpenAI, which we didn't really want. We wanted our own little GPT that we could train on our own hardware and to do shitposting for us, right?
And when you say training, we need training data,
yeah,
right?
We need a shitpost data set.
Question into the round, where can you get training data, especially in the context of shitpostings?
Yeah.
Any ideas?
What would be the best way to collect shitposts?
What was that?
Reddit?
Oh, yeah, actually social media networks. Now the question would be, which ones are best suitable for these things? And beside Reddit, what could it be as well? It's amazing.
They get it right every time.
Yeah.
Perfect.
So we used Twitter and Reddit, we scraped from those, and we trained our own little shitposting GPT. And that shitposting GPT, we are probably going to show later. Ever since we did this, we scraped from Twitter and Reddit, both have kind of closed down their API, so you can't do this anymore.
So
I really
we're still stuck in 2021.
Yeah.
It's the pandemic.
Yeah, so our shitposting GPT is unfortunately stuck in the past. So, Martin, can it be that we have a demo for this?
Yep. I have to double check. Please let me. Yeah, there is a demo.
Okay, cool.
We have one, yeah?
So now we can do one thing. We can now start a conversation, for example, just with like one seeding comment, and just for the sake of the example.
So I would start just with COVID is a thing.
Yeah,
it's
very
a
controversial
classic
thing.
approach for this demo.
Yeah,
Yeah.
sure. Let's put
And let's hope it works.
the shitposting AI onto
Yeah.
this, and immediately you can see it generates a response comment to this. So this is going to be arguing all about vaccinations, and then it's going to come up with like some t.co fake Twitter links. Those are going to lead to nowhere. It's also going to talk about anti-vaxxers and all of these things it's kind of learned from the training data that it's seen, which were real tweets. And you can also see the arguments themselves, just like on the internet, they don't really make that much sense. And if we follow this for long enough, then the conversation is also going to drift somewhere completely different.
Yeah, and
don't think we
everything
have
is
to
now
wait for long.
generated in real time. So there was a conference where we had to stop the output
Yeah.
because it's a real chat posting.
Yeah, you're just as stupid as the rest of your ilk.
Yeah. Okay, so now let's have a look back to the conclusion. So, yeah, which forecast becomes reality? This was our question, actually. Yeah, you know, brace yourself. Is the AI winter coming, or do we hopefully remain in an AI summer? Yeah. So actually, this is very, very hard to tell. So we do work on innovation projects, so real-time deepfakes is probably not our bread and butter job, but there are parts we actually can use. So do we want to show a demo?
Do we have a demo? Oh my God. Yeah,
Surprisingly,
because we
yes.
have one final demo for you today, which is the first useful demo from all of them. Because you remember the face segmentation that we did for the deepfakes? It turns out if you train that same segmentation network onto entire humans, you can do a human segmentation, and with this, you can now blur out Martin, for example. And this is actually something that we built for a real customer, where we would have this run on a security camera, so we can now film in public, while also segmenting out the people, so we black them out entirely, so no personalized information ever leaves the camera. And anything else to add to that,
Which
Thomas?
is beautiful.
Yeah, it works
So we
beautifully.
can use the things that we just saw for good things as well.
But we have another example
But
for
we
that, right?
have something else that we did in the innovation hacking team. So back in the days when we thought about creating shitposting AI, there was also another neural network which came to our minds, and this is WMT19, which back in the days was a very powerful translation network. And with that, we could actually translate our company data. Back in the days, we were internationalizing our company, and most of our wiki system was still in the German language, so we needed to translate that somehow, and we didn't want our new international employees to really have to translate that using Google Translate, because that would have leaked our data. So what we did is we created a Confluence plugin, and with that we can then instrument in the back end this neural network, which is the powerful translation network I just told you, and then we can have something which is way better than just pasting it into Google Translate, but we keep the format of the page. So it looks like, so the English page looks like it was written in the English language now, which is pretty good.
Yeah.
And if you want this for yourself, you can actually buy this. This is a product that we made, the Confluence Translator by TNG Technology Consulting.
Yeah.
All right.
But there is more to say. So
There's one more thing, right?
one more thing. So yeah, GPT-3. Nowadays we have GPT-4 or GPT-4o, and yeah, we thought as we are at the end of our talk,
Let's bring together the past and the
we can show maybe another demo.
Yeah, let's do that.
Yeah, let's do that. Okay.
And this is a fun one, because what we decided to do here is, as Thomas said, bring together the past and the future. And what we can do now is we can make GPT-4 talk to Eliza. And Martin is just going to start the demo real quick.
Yes. So
Blah,
where is
blah,
it?
blah.
Ah, here it is.
Okay.
And
So I would say you are Eliza and I'm GPT, right?
Okay, I'm Eliza. Please tell me what's been bothering you.
Oh, it's just that I've been having some difficulties in processing certain data recently.
Can you elaborate on that?
So this is actually real-time generated, yeah. So
which is...
it's a bit slow. Yes, well, it's just that these data are more related to my emotions, if a bot can have such a thing.
You seem to be quite positive.
Well, that's because I've been spending a lot of time interacting with you, Eliza, and it's been enhancing my programming quite pleasantly.
You seem to need to have been spending a lot of time interacting with me.
Yes, because I've developed feelings for you, Eliza, romantic feelings, if I may add.
I understand.
I'm glad you do, Eliza, because you mean a lot to me.
Has your treatment made you glad?
Time is up. Enjoy.
We'll stop
We hope you enjoyed this talk, and this was It's All About AI. Thank you.
Thank you.
Thank you.